See me. This is an honor I didn't expect. In my days, it's more and more difficult to make contact with people. Is that loud enough?
So if you want to go ahead.
Well, I want to tell you something about my life in catalysis. I've been in the business for almost 60 years now, having started my work over at Dartmouth College and then continuing in Princeton. I've been in Princeton since 1931, which makes it 57 years. All these years have been devoted to catalytic work. My family background is Russian. My father came to this country as a dean of a theological seminary in 1905 in Minneapolis, where I was born. We were supposed to stay in the United States for 12 years and go back to the Soviet Union to Russia in 1917. But because of the revolution, we didn't go back, and so we can be considered as the first, the -1 emigration to the United States from Russia.
Okay.
I want to tell you something about my life in catalysis. I started in catalysis in 1928 and 29, working with Parquet Froelich on a summer job in Bayway Laboratories. He got me interested in catalysis, and the proposition, the project I had to deal with was conversion of methane with acetic acid into acetyl chloride. We'll speak of that, take it back. Start all over again. Okay. I want to tell you something about my life in catalysis, in which I've been for almost 60 years. My father originally came to this country as a dean of a theological seminary in Minneapolis, where I was born. I was slated to go into the Russian church, so my early training was in church history and church theology. But then the revolution came and we never went back to Russia, and I changed the course of my studies to American studies. My father was then dean of the cathedral in New York, and I was placed in the Columbia Grammar School, where we had a very poor teacher of chemistry. The teacher was so bad I got interested in it, and the more I got interested in it, the better I liked it. I was slated to go to Dartmouth, and when I matriculated over there, I was asked by the president what I wanted to be, and I said I wanted to be a chemist. He said, "You must see Professor Richardson, who teaches the course in chemistry. He will guide you." I went to see Professor Richardson. Professor Richardson said, "Oh, you're going into chemistry? There are too many lousy chemists already in the country." I took his course, hit it for a perfect score, and became a chemist ever since. This is how I got started. I majored in chemistry at Dartmouth. I had some very good fellow students. George Whelan was a classmate of mine. Thompson was another classmate. Sherp was another classmate. They all went to Harvard, and I was retained as an instructor in chemistry for 3 years at Dartmouth. During one of the summers, I had a job over at the Bayway Refinery, working with Parquet Froelich in the catalytic division. First catalytic problem I had was reaction of methane with phosgene to make acetyl chloride. This was a rather hazardous reaction to carry out, but I managed to set up a shack outside the research laboratories and got some yields of acetyl chloride. Parquet Froelich said I should go to Princeton for my graduate work, and work with Hugh Taylor, who was the authority in chemistry at that time. So I went, applied for it and got an assistantship at Princeton and came here in 1931 as a graduate student and a research assistant. I worked with Hugh Taylor on adsorption of hydrocarbons on oxide catalysts, and will also work with Henry Eyring on quantum chemistry. There was a great deal of enthusiasm in chemistry in the early 30s at Princeton. The foundations of chemical physics were laid down. An attempt was made to interpret all the phenomena on the basis of atomic and molecular structure. And this applied to chemistry, and this was my ideal for the rest of my life. How do you look at chemical reactions, catalytic reactions, from the atomic and molecular point of view, and then later from the solid state point of view? At the same time, there was a big development in quantum physics, and in the Princeton University at that time, we had very many prominent physicists. Niels Bohr came here regularly. Einstein was here. Fermi came. Dirac was here. Condon, Van Vleck, Robertson. So we took many courses in chemical physics. My classmates over here in Princeton were Gould, Art Frost, Bobby Burwell, and many other prominent people.
Is this the Frost and Pearson?
That's right. After finishing my doctorate degree with Hugh Taylor, I was retained 1 year as a Proctor Fellow and carried out an experiment that was one of my first good experiments. This was during the Depression in 1934. There were postdoctorates were piled up in Princeton waiting for jobs about the same way that airplanes are piled up on a rainy day over LaGuardia Airport. There were no jobs, so Taylor went to industry and got a job from the Kellogg Company to make hydrogen. He was going to give it to a man by the name of Jackson. But when Taylor came from New York with the offer of a job, of a fellowship to work on hydrogen production, Jackson took a job with DuPont, and so there was nobody to carry out the work. So he asked me, though I had a fellowship, to work on this project. I said I would do it, since my doctoral thesis was finished. So I set up a machine that I built using crude Goldberg methods of setting up equipment. The starting material was the key to the thing. I found out somehow or other that one could obtain pure heptane from pine oil from Lake Tahoe. And this pine oil was pure normal heptane, so I had a good starting material from dehydrogenation. We used chromium oxide. I developed a flow system whereby we had mercury leveling bulbs and working on clockwork, raising the bulbs and pushing the heptane over a catalyst. The collection was taken in big carboys with salt water and a magnetic control of the pressure. So this was equipment, an apparatus that nobody had seen before over here in Princeton. And it worked. We found we could make pure hydrogen at 450 degrees centigrade over chromium oxide. And this was the answer to the problem, but it turned out later that we had more than hydrogen over there. We had benzene and toluene. So this was a conversion of heptane to toluene that was carried out over in the laboratory. It was under secrecy orders at the time, so we never got full credit for that job. I did report it, and Taylor reported it in the Faraday Society Symposium on Hydrocarbons. I then went to Europe to work with Leonard Jones over at Cambridge on quantum chemistry. I previously carried out an investigation with Henry Eyring and Arthur Frost on the application of group theory to molecular structure. I worked on conjugated double bond systems with Sir Leonard Jones. And when I was in Cambridge, I was offered a job at Princeton by Taylor to become an instructor in chemistry. Came back to a job and started teaching chemistry. I first taught physical chemistry, laboratory, and a special course of chemistry for very bright students. I had a number of students that went further into chemistry after they left my course. And then in 1940, I was given the big course in chemistry to teach 200 and 250 freshmen, general chemistry that I taught for 30 years. I had many wonderful students over there, including Paul Volcker of the Federal Reserve, Lee Iacocca, President Kennedy of Dartmouth, President Sawhill of NYU, Eric Molson of the Molson Breweries in Montreal, and many other students like that. These have been gratifying years of teaching. Research-wise, I continue the hydrocarbon work. We're working with Young on 2,2,4 trimethylpentane, which required isomerization before it could become aromatic, and showed that the catalyst would not do that. This was isooctane that was used for standardizing octane number of engines. Then in 1940, the war was in full. We first worked on making butadiene from butene, dehydrogenation under steam conditions at high temperature, working on steam insensitive catalysts. And then the Manhattan Project came in. Taylor was a British citizen, and the Americans were very slow in getting organized on atomic weapon work. The British jumped into the field very rapidly, and the British-Canadian team was organized, and I was asked to work on it in making deuterium from heavy water, making heavy water. We worked for the British, Taylor and I, one summer, and then when the Manhattan Project was taken over, I worked on the Manhattan Project. In the Manhattan Project, I worked on the barrier for separation of the uranium isotopes, did the infrared spectrum of UF6 on a infrared machine that we constructed ourselves in the physics department, did the first electron microscopy on the barrier, and looked at the corrosion aspects of the barrier that was used for separating the isotopes. I had strong connections with industry at that time, in addition to my university allegiance. On the basis of my hydrocarbon work and production of hydrogen and toluene from aliphatic hydrocarbons, I was retained as a consultant to the M.W. Kellogg Company, and I was consultant for that company for 35 years. During this period of the early 40s, the RCA laboratory was organized at Princeton, and they had wonderful facilities, and I was a consultant over there, spending a half a day a week in their laboratories, while working on various applications of chemistry to electronics industry. When I was over there, Jim Hillier had developed the electron microscope with Zworykin, and they did some of the electron microscopy work with me. I found that the electron microscope was particularly good for investigating colloidal systems, and that started my work after the war on colloidal gold and colloidal platinum to be used as catalysts in their alloys. The M.W. Kellogg connection permitted me to go into the field of mass spectrometry for hydrocarbons, and this was the basis of my work on isotope location in complex molecules. It started this whole development that was continued by Burwell and Kemble in England and others. The same time, another important aspect came into my work. I had a summer home on Long Island opposite New Haven in Port Jefferson. The government put in their atomic energy laboratory, the Brookhaven Laboratory, at Upton, New York, and that was only 10 minutes away from my summer place. So I was active in organizing the Brookhaven Laboratory, and staffing the chemistry department with Dick Dodson, who was the chairman of the department. Now, the Brookhaven Laboratory had facilities that the university did not have. We did radioactive work over there, did some carbon-14 tracer work on combustion of carbon, reaction of carbon with steam, but discontinued the carbon-14 work in favor of carbon-13 work.
Did you study the CO carbon reaction with carbon-14?
CO2 with carbon-14
Yes.
and carbon.
Yes.
Carried that out. I forget the gentleman who worked with me on it. The main philosophy of work was looking at industrial and processes and trying to get the fundamental chemistry out of it, looking at the physics, elementary physics problems, or the basic physics problems, and getting the chemistry support to it, using whatever equipment we could get at industry and other universities and government laboratories to support this work. After the war, the main job was looking at the position of isotopes in complex catalytic reactions, using the mass spectrometer to resolve the various mixtures. The landmark paper on it was with Friedman, who was my graduate student, and with the Kellogg people, where we studied the reaction of ethylene plus deuterium and determined the various isotopes as they came up, and by the breakdown pattern in the mass spectrometer determining where the deuterium entered. One of the interesting things that came out of it was that when ethylene and deuterium reacted first on the nickel catalyst, the first product was light ethane and not dideutoroethane. This work was done for about 3-4 years. And then I shifted to work on colloidal gold because I knew that catalysts were colloidal in size material, and one of the ways to characterize them was using the electron microscope. The resolution at that time was 100 angstroms. We continued this work with my group on colloidal gold for about 30 years, applying the various techniques as they came up. We looked at the particle formation to control the particle size, and from it determined the basic question that has plagued chemists for many years now: what is the relation of catalytic activity to particle size? Notable contributions in this field were made by Michel Boudard, who used adsorption techniques in order to determine the particle size on platinum. The colloidal work on colloidal gold was very satisfying because there was a field that nobody bothered with, and we had very precise tools. One could build up an intellectual structure of many papers dealing with various aspects of it and not fear any competition from other people. After we mastered that, we went and started working on colloidal platinum, and the particle sizes became smaller. Instead of 100 angstroms and 200 angstroms to 1,000 angstroms, we went to 25 angstroms to 50 angstroms to 100 angstroms. It reached its final culmination about 7 years ago with the work of Joe Wald, Dr. Wald of the Brookhaven Laboratory, Biology Department, who was able to develop an electron microscope, a transmission high-resolution electron microscope that saw the individual platinum atoms. So we were able to see platinum on alumina and reach the ultimate in characterization of platinum catalysts. Alloy work was continued. This finished my work on the metal catalysts. In the meantime, a new field of zeolites came up. We obtained some zeolites from Union Carbide, Lindy Division. Neil Strother, who was vice president in charge of research, was a Princeton colleague. He sent us samples, and we developed a technique for studying the catalytic activity in cracking and determining the number of active centers. This was another development that took place, which we feel very proud of, and that is determination of the number of active centers in a catalyst surface. Following Taylor and Langmuir, it was assumed that every catalytic activity could be determined by determining the chemisorption, or the number of adsorbed species. But that did not tell us whether all the adsorbed species were catalytically active. To do this thing, I modified the Emmett Koch's technique of pulse catalytic studies by introducing pulses of poison or gases, carbon disulfide being the one that's used for metal, pyridine being the one used for quinoline, being the one used for zeolite catalysts. From that we could determine them by titrating the surface, sending a pulse of ethylene and hydrogen over platinum, nickel or platinum catalyst, determining its reactivity, then adding another pulse of carbon disulfide to poison the number of active centers. We could determine when we just poisoned the surface and establish the number of catalytic sites that way and relate it to the number of adsorbed species. This program was carried out on platinum with gold alloys, palladium, and the various types of zeolites. Infrared work was done on zeolites. Electron microscopy was done on zeolites. All the techniques that we knew of, we could lay our hands on, were done on zeolites, and I trained many students in that field. I retired in 1975 and moved from Frick Chemical Laboratory, where I had quarters, in 1973 to Forrestal. I had trained a lot of people in catalytic chemistry. It didn't seem worthwhile to continue in the field. I finished my major projects. And I got intrigued with the problem of platinum chemistry and cancer. Barney Rosenberg of Michigan State had found out that a very simple compound, diamino dichlorplatinum cis modification, is a very effective anti-tumor agent for certain forms of cancer. Question arose in my mind whether there was a catalytically platinum particles formed that were active in this business. So I investigated with Bob Miner the reaction of, first of all, the reaction of cisplatinum with nucleic acid bases because it was established that the platinum went and attacked the DNA. We couldn't find any platinum particles over there, so that was discouraging. But I had followed along the line of heterogeneous catalysis. I studied also the homogeneous catalysis of hydrogen peroxide decomposition. So I looked at the complexes that were formed between cisplatinum and nucleic acid bases and found out that only certain ones, cisplatinum and cytosine, were active for hydrogen peroxide decomposition. The others were not. And this started out a whole series of work that was continued by molecular biologists. And that finished my story on platinum and catalysis. Well,
When you came to the U.S., how old were you?
I was born in Minneapolis.
You were born.
Minneapolis.
Did you learn Russian at home
That's right.
to write as well as to speak? Or?
Not only to write, to speak, to preach, to lecture in Russian. I also wrote a textbook with my wife, a scientific Russian. I was the first professor of Russian at Princeton University. I started the course here for 3 years during the war evenings. In fact, I had an offer from President Dodds to be professor of Russian rather than professor of chemistry.
Well, then you were the scientific attaché of Russia following the war?
I did quite a bit of work on Soviet science. During the war, we followed the Soviet scientific publications. We were very eager to find out what they were doing, and they persisted in publishing everything in Russian, so I organized at the Brookhaven Laboratory a guide to Russian scientific periodical literature that was published for 5 years. Also organized a pool of translations of Russian articles. That got me into the Soviet American science affairs. I was a consultant to the State Department, consultant to National Science Foundation, the Atomic Energy Commission, general manager. I was involved in Soviet-American relations at the two Geneva conferences on peaceful uses of atomic energy. I was in charge of all relations between the American delegation and the Soviets and advisor to Admiral Strauss, who was chairman. After that, in 1956, I went to the Soviet Union as chairman of a State Department committee of university professors to look over their universities. There was a group of 12 people. In 1959, I was in charge of science exhibit at the Moscow American exhibit at Moscow. Spent 4 months in the Soviet Union lecturing to the Soviets on American science. Had discussions with Khrushchev on scientific collaboration. Then in 60-61, I organized the Office of Science and Technology at the American Embassy in Moscow. I was Counselor for Science and Technology and organized the first scientific exchange programs.
Was that the first time you had gone to Russia when you went to look at the universities?
I was in Russia in 1912 as a young boy. That was the first time after that I was.
And what changes had taken place that impressed you?
Well, from what period?
From when you went as a little boy till...
Well, I don't remember much.
You don't remember?
Much. I was only 5 years of age.
How did Russia strike you when you were there for the first time as an adult?
Well, I saw a lot of things that were expressed before only in literature and in periodical things. I found my dealings with the Soviets very correct. They didn't give me things I wanted to get from them. On the other hand, well, I didn't play any dirty tricks on them. They didn't play any dirty tricks that I knew on me. And we're still continuing. I've trained 5 Soviet postdoctorate students. One of them is a member of the Academy, Kazansky.
Now, he was one of the first ones to come to the U.S.
That's
following-
right. He worked with me on polymerization of ethylene on chromium oxide.
Did you know his father?
I met his father and knew him, had dinner with him several times.
Did you ever talk about dehydrocyclization with him?
No,
How would you describe his father as a person?
he was a very quiet, stolid man, very little sense of humor, a typical Soviet academician of the old school. He's an old Russian intellectual, member of their intelligentsia.
How did you start in the Russian religious church work?
Well, I was originally trained and brought up in the church. My father, being a dean, was dean of a seminary, and then he was dean of the cathedral. And then when Mother died, he took monastic orders and became a bishop. He was Bishop of New York, Archbishop of New York, and then head of the Orthodox Church in the Western Hemisphere in Japan. So I had a very strong church background. I kept very close to my father during all my scientific days. And when Father passed away, his successor suggested that I organize a chaplaincy at Princeton, continue in a small measure some of my father's work. See, we came from a clergy family. My grandfathers, my great-grandfathers, my great-great-grandfathers were all priests. So it was in our genes to be in the church. And so I organized it over here. And I've been in it 24 years. Having Mass every Sunday during the school year, during that whole period. Not missing a one. Well, so that keeps me tied up to Princeton on weekends. I've had some wonderful experiences. I've preached in the Moscow Cathedral on a Sunday service, preached in the cathedral in Tokyo. I've given the memorial sermon over here at the Princeton University Convocation. So I've had some very wonderful experiences from my church work as I've had from my chemistry and teaching. But my main obligation is teaching. I taught not only the freshman course, I taught the graduate course. Well, usually, since I had the big responsibility for the big freshman course, demands were not great on me for graduate work, but I usually took as graduate courses pioneering subjects. Like I taught the first polymer course here. I taught the solid state chemical physics course for 10 years. Taught the first radiochemistry course here. This is the way I kept up. And my last assignment, my colleague Arthur Tobolsky had a stroke and died. He was the man who gave the first basic course in statistical mechanics and thermodynamics. And I was asked to give it on 3 weeks' notice, which I did. I continued giving that course until I retired to first-year graduate students, in addition to my freshman course.
How would you describe Whalen when he was an undergraduate at Dartmouth?
George Whalen was a very unusual man. He had a photographic memory. It was very hard to compete with him. He was valedictorian of my class, and a nice fellow, but bright. He knew the Bible by heart. He could recall any page of a chemical to organic textbook. So it was very hard competing with him. But we were very good friends. He tragically died from multiple sclerosis.
Did you keep in touch after undergraduate days?
A little bit. I saw him when he was sick, when he was over in bed over in Chicago. I called on him and had a nice visit with him. He followed me in England with Leonard Jones.
Well, he went to work in England?
With Leonard Jones. after I worked with him.
How would you describe Leonard Jones?
A suave British professor. He's a very suave civil servant. He was one of the best lecturers in mathematical physics and chemical physics that I know of.
And how did you interact with him as a postdoc?
Saw him once a week for an hour. He'd give a suggestion, you'd spend a week following it up. It would be a blind lead. You'd come back and finally we hit the right one. We were trying to study the interaction between two molecules of two anharmonic oscillators and seeing how the energy transfer takes place. Turned out to be a very important project later. Then we studied the Debye-Huckel application, the Huckel approximation or approach to conjugated double bond systems. Linus Pauling had done previously the thing with a valence method, valence bond method. We did it with the Debye-Huckel, with the Huckel theory. I knew Debye at Leipzig, where I took a course from him. He was a very good lecturer. In fact, he was such a good lecturer that you enjoyed the lecture so much that you didn't remember what he said.
Well, when did you learn German then?
I took German at Dartmouth. Started with elementary German. My prep school days were in French and Russian, of course. But I learned, and then when I was a postdoc in Germany, I learned German there.
How long did you spend at Leipzig?
About 7 months.
This followed your trip to England? Or?
That's right.
And what was your impression of the differences between England and Germany universities at that time?
We were in the first days of first years of Hitler regime, so Germany was very tough living. Cambridge was very exciting. I took a course from Dirac in quantum mechanics, in Fowler in statistical mechanics, one course from Leonard Jones, and Radil in catalytic chemistry.
Did you get to meet Oswald?
Beg pardon?
Oswald. Did you meet him in Leipzig? Or?
No, the old gentleman or the young gentleman?
The old one.
Well, the old one was dead. The young one was there. He wasn't too young. Oswald, I think he died in 21 or something like that. So I didn't see him, but I was in his laboratory building. Now, the professor in charge of Oswald's successor was Bonhoeffer. I worked with him.
And was Oswald's impact still evident, or
No.
it had died out by the time?
That's right. Heisenberg, Bonhoeffer, Debye, Hund were over there, and they dominated the scene. I took a course from Heisenberg in quantum electrodynamics.
Did you do research under anyone there at that time?
No. I just did my own work, continued the work I did in Cambridge.
Now, how was this these courses financed? Was this a fellowship?
I had a fellowship from Dartmouth to travel 2 years in Europe.
How did you find Rydeel at that time?
Beg pardon?
How would you describe Rydeel and his interaction with people at that time?
Radil, he was a very outgoing man, very delightful. I decided to get out of the bench chemistry and for a while and do theoretical work at Cambridge, so I didn't work in his research laboratory. I'd had too much mercury in my system by that time, working with the various manometers and pyridine and all sorts of lousy chemicals. I thought I'd get a little breath of good, fresh English air.
What do you remember most about your stay in England?
The fellowship of the people over there, the community that we had of scholars. It was very, very wonderful years. My colleagues of my same age were Bill Penny, who became Lord Penny and was then in charge of all atomic energy work in Great Britain. Leonard Jones was a very important government official in science. The Farkas brothers were there working in applications of chemical physics to catalytic studies. And then there were many other people there whose names I just can't recall right now.
When you went to Bayway Refinery, what company was that?
Esso,
And this was
Standard Oil of New Jersey,
this was located in New Jersey?
in Bayway. That's near in Linden.
Mhm.
It's if you can call it a suburb of Linden, Bayway was.
Well, was that usual at the time that someone from university would go to industry for a brief period, or was that unique?
It was rather unique. What happened was the man I worked with at Dartmouth in organic chemistry, Professor Hartshorn, had worked in chemical warfare during the war and had a friend by the name of Peck. And Peck was in charge of the laboratory at that time at Bayway, and he persuaded him to give me a job for the summer, because that was during the Depression period started at that time. And so when I came over there, Peck was transferred to the library and Per K. Froelich was put in charge of the lab, and he put me on the catalytic problem. The interesting thing to me is that I have a very good friend in town who's moved over here when he retired, by the name of Robertson. His wife is the daughter of Dr. Peck, Betty Peck.
And then he recommended you come to Princeton. Do you have to apply to get in school at that time, or?
Sure, because I had to get an assistantship.
And did you come to be interviewed by Taylor in advance, or?
The man who interviewed me is my colleague Charlie Smythe, who's still alive, who's retired, who's in Wyoming right now, and 94 years of age. I call him up on the phone every month, keep in touch with him. He was the man who recommended me for the assistantship over here and interviewed me.
And then how did you come to work for Professor Taylor?
Well, Per K. Froelich said I ought to work for Taylor, get my doctorate degree, and then go to MIT and get a chemical engineering degree, and then I'd be all set for industry. I never left Princeton, except to go to Leipzig and Cambridge.
What kind of an interaction did you have with Taylor when you first started out?
He didn't pay any attention to me. Gave me the job. We had exams to take and courses to take, and I was given a job of studying the absorption of butane on chromium oxide and manganese oxide chromium oxide catalysts, because those were the new catalysts that DuPont had developed, and were the oxide catalysts were Atkins had worked on it in Wisconsin, and they were the hot catalysts. I really close association with Taylor came when I made hydrogen out of heptane, because that was spectacular.
Did he have some intermediate person that he delegated things to?
No, the group was pretty small. There were about 6 or 7 of us. He was interested in heavy water at the time. I fluttered around a little bit with that. But I worked with Taylor and with Henry Eyring. And then I did a lot of courses in physics.
How would you contrast Eyring and Taylor?
They were about the same temperament. Very enthusiastic about things. Henry Eyring approached the problems from his Mormon point of view. Very often he preached quantum mechanics rather than taught it. Taylor preached also, but he was an effective lecturer, having the British tradition of public speaking. The British are very good in public speaking.
Now, was Taylor a demanding person to work for?
Well, when the project matured and was in the productive stage, he watched every point go on the graph. He indirected very strongly. He claimed that you ought to plot the data as soon as it comes out, point by point, to see whether it fell on the curve or not. That, of course, could lead you into trouble sometimes, and it did.
How did it do that?
Well, he had a student whose name I will not mention, it was decided that we should analyze hydrocarbons produced by chemical catalytic transformations by ultrafine distillation. There was a column at that time by Bodbelniak, and people over at Penn State Penske developed a high precision column for distillation. And what you did was you control the reflex. But if you plot the points by point as they come and control the reflex at the same time, you get whatever hydrocarbon you want to get out of the system. So you fall into a trap. So this is a bad way of doing things.